The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
I would like to introduce the first speaker and the topic that will be the WindEEE Dome demonstration of successful implementation by Marwan Kishek of NORR Engineers. Marwan, Dr. Kishek, is a seasoned professional engineer with extensive experience in leading structural teams on high-profile education, healthcare, commercial, municipal government, industrial, recreational, and residential projects. He has over 20 years of successes as a senior engineer, senior project manager, working with top caliber Canadian and American firms. Now I would welcome Marwan to start with this topic.
Thank you, Neil. Good morning, ladies and gentlemen, and welcome to the ACI convention. I trust that you are as excited as I am for being part of this event. I will start with a brief introduction, followed by an overview of the WindEEE Dome facility, with a discussion of objectives of the design team and the benefits of the role that BIM played in realizing these objectives. And I will then go into a little bit of detail as to the software used on WindEEE project and the description of the structural system. And then I will wrap up with snapshots from photos during construction to illustrate some of the points that were made in this presentation. As a demonstration of the successful implementation of BIM, the presentation will showcase the WindEEE Dome facility. This facility belonged to the Wind Engineering, Energy and Environment Research Institute at the University of Western Ontario in London, Ontario, 2 hours west of Toronto. I will focus on the implementation of BIM in the design in a multidisciplinary environment during the design phase. The architect of record for WindEEE is NORR, international multidisciplinary firm that provided architectural, structural, electrical, and mechanical teams and worked very closely with specialty consultants and stakeholders to design this one-of-a-kind facility. My role on this project was to lead the structural efforts during the design and the construction phases. The WindEEE Dome is the first research facility of its kind in the world, designed to simulate a variety of wind conditions that present wind tunnels cannot perform. A conventional wind tunnel usually evaluate the stress and pressure on buildings created by a single direction wind stream. In the new WindEEE Dome facility, it will have the capability of producing or simulating high intensity wind systems, including swirling and multi-directional wind that characterizes the localized wind systems such as tornadoes, downburst, wind shear, and other wind effects. The WindEEE Dome will be used to study the effects of local wind systems on the natural as well as the built environment under one roof. The $30 million facility will also be used to understand the impact of these local storms on buildings, on structures, on forests, and on crops. And also it will be used to improve the positioning of and the design of wind farms, and to study the pollutant and contaminant dispersal. The simulated wind will be achieved by a complex array of fans arranged around a hexagonal test chamber, the inner hexagon in the image. Each of the walls of the test chamber will consist of a steel rack with a number of fans inserted into this, so the fans will be rotated and so on to create the different wind effects. A total of 106 fans can be manipulated to simulate winds ranging from hurricanes to tornadoes, microbursts, and downbursts. Each fan is controlled individually and can be accelerated or deaccelerated within 1 second. The building itself is arranged as a domed hexagonal building housing the test chamber. So we have an outer dome and inner dome, and there is an attached two-story research building next to it, as you see in the image. The three-story hexagonal building is a reinforced concrete structure with a steel roof, and it is designed to integrate the architecture of the building with the specialized equipment that creates the various wind conditions. The outer building shell is 40 meters in diameter, around 133 feet, and the inner shell is 25 meters in diameter, and the space between the outer and inner shells are used to recirculate the air. The main objectives of the design team were to provide innovative and durable solutions and deliver a design that will serve the various functions of this versatile research facility for many years to come. It was very crucial for this unique project to ensure best fit and integration of the specialized equipment and tested chamber that were designed by the specialty consultants within the building that was designed by NORR teams. The use of BIM as the main project delivery method significantly contributed to these objectives by greatly enhancing the collaboration between the various disciplines, architecture, structure, mechanical, electrical, as well as the specialty consultants and the stakeholders to deliver an iconic facility. In addition, with so many sleeves and penetrations through the concrete work required to serve the specialty equipment, BIM played a big role in ensuring clash detection during the design phase and avoid potential costly changes and conflict during construction. Building information modeling is a new approach to design, construct, and manage buildings and infrastructure. In a nutshell, BIM can be described as the process of generating and managing building data during the life cycle of the building using 3D real-time dynamic modeling. A BIM model is essentially a virtual object database shared by AEC partners. It connects the 3D forms to non-graphic attributes such as material properties, schedules, costing, and performance information. Sharing a central BIM model by multidisciplinary project teams enables any team member to access information from other disciplines. As such, teams are able to make more informed decisions earlier on in the design planning process when decisions have the most impact on schedule and sustainability. Furthermore, consistent information reduces misconceptions, while better coordination and clash detection reduces errors. In BIM, when changes are made on a project, all the consequences of that change are captured and coordinated throughout the BIM model, including the drawings generated by BIM model. Changes and revisions of designs during the lifetime of the process are therefore easier and faster to implement. Inherent in BIM is the ability to generate schedules, costing, calculate program areas and spatial relationships, and quantities, and specify properties of building components. It is important to note here that an ever-increasing number of governmental and private clients, including the big chain companies, are requesting BIM as the only delivery method on their projects. NORR architects and engineering teams utilize REVIT from Autodesk as their BIM software. REVIT structure, REVIT architecture, REVIT mechanical, and REVIT electrical were used by the various disciplines. The specialty consultant, though, used a different BIM software called PRO-E. And I believe the name has changed recently to another name. The REVIT modules are interconnected. As you can see, all the REVIT modules are interconnected with each other through a central shared model. As also, we were able to connect the PRO-E also to that model. So we could. There is an advantage in this system, of course, that the individual discipline has control over their model, yet at the same time the contents of that discipline's model can be shared by other team members. The REVIT structure, let me talk a bit about the REVIT structure, is also interfaced with structural or engineering design software, design and analysis software, such as STAT, structural system, ETABS, SAP, and STAT Pro. And the model can either be created in an engineering software and exported to REVIT, or vice versa. Anytime the REVIT model undergoes any changes, it can be exported to the engineering software for reanalysis and redesign, then imported back into REVIT with the updated design automatically captured through the model through the REVIT model. Yeah. In this slide, we can see the individual models. So we have REVIT structure, REVIT architecture, REVIT mechanical, electrical, and then the PRO-E model for the inner dome or inner chamber, tested chamber. And all of them can be combined or integrated into one integrated model, which we'll see in the next slide. This is a section cut through the integrated model. As you can see, having the equipment, the structure, the architecture, the mechanical, electrical, all in one model will make it easier to detect any clash or and even you can understand how things fit together more. Take off, we have calculated or automatically calculated the steel, structural steel, excluding the miscellaneous steel, is about 220 imperial tons. The concrete takeoff is 2,000 cubic meter. That translates into 2,700 cubic yards for those who use imperial units. And I would like to note here that the accuracy of the BIM takeoff depends on how much the model is detailed. For instance, if you detail the miscellaneous steel, you can calculate the takeoff for miscellaneous steel. If you would like to have the takeoff for the rebars in the concrete, you need to model the rebars. In WindEEE project, the rebars were not modeled due to time constraint, but they were drawn conventionally on sections generated by REVIT. Also, from a civil engineering point of view, the The building coordinates were established through the Geospatial Consortium using GIS, Geographic Information System. This enabled the building to be strategically located or placed in REVIT to take advantage of the sloped sites, so that the road, a road for truck access, which we'll see later why we need the truck access, was established at the second level, and the main entrance was made at the lower level. Now the truck access is needed so that wind turbine blades can be tested while mounted on a truck. So the truck drives in front of an open overhead large door, and the blade will be tested by simulated air coming from inside the building to the outside of the building. This is another blueprint generated by REVIT. Again, this is from the integrated model. And you can see the equipment, the test chamber, and the building shell. The structural system for this building, for the 3-story hexagonal building, consists of reinforced concrete construction that houses the main test chamber, mechanical, electrical spaces, etc. The building features a hexagonal steel dome as well, spanning 40 meters, and the dome was designed for also, in addition to snow, wind, and seismic, it was designed to carry the hanging load from the upper test chamber. This is the analysis and design software linked to REVIT was used to design the steel dome and the structure. So the steel dome was designed in STAAD Pro. This is an earlier version when we had overhangs for the dome that were eliminated during a VE process. And again, the interface between REVIT and STAAD helped in make the implementation easier. Reinforced concrete components such as slabs, columns, shear walls, and foundation were designed using E-tabs and S-concrete. And now we'll scroll through some photographs during construction just to give you an idea about this is the basement or the ground level, and the center opening is a 20 meter in diameter, and this will be infilled by the floor of the test chamber. It's a specialized floor that will be supported by the middle columns, the 4 columns in the middle, and by the slab edge around the perimeter. In this photo you see the second floor, and this floor will support the 6 walls that carry the fans and the test chamber itself. In this photo you can see the tension beam. We have designed a tension beam to take the thrust from the trusses, and the amount of thrust we have is 500 kips, around 2,250 kilonewtons. We also designed 6 reinforced concrete buttresses at each corner of the hexagon. On the right hand you see the buttress. Also the buttress carry a part of this thrust from the reaction of the truss, plus shear and seismic, and shear from seismic and wind. This is the detail of the buttress on the detailing of the buttress on the right. We designed that as a strut and tie to take the reaction from the column of the truss. Here we can see some slides that show the interface between the ceiling of the test chamber and the buttresses or the concrete building. And you can see how so many sleeves in this project that were coordinated using BIM, and in addition to some embedded plates and so on. This is a shot that shows you how the trusses are pushing on those buttresses. Okay, the construction of this facility is slated to be completed by the end of this year or early in the next year. In this shot, we see the upper test chamber, which supports the six large fans and is hung from the roof. There's significant hanging load from the roof. This was constructed on ground because it's as heavy as like 60 tons of steel, and hoisted in place. So they build it inside the big dome, and then they hoist it into place. This is during the hoisting on the left, and it was hung from 12 hangers, two on each side of the trusses, and you can see it fits because this is all bolted connections. Any lack of accuracy, you don't get that effect. So we got an email from the University of Western Ontario saying it fits. Please recirculate this photo. Again, the completed upper chamber with the 6 fans, you can see 2 of them, huge fans with catwalks to service them and so on. All of this is hung from the dome. This is the the overhead large opening that I talked about earlier. The truck drives is, with the blade positioned in front of the door, and the simulated wind is blown from the inside to the outside to test this blade. It will, of course, will have all kinds of gauges and so on it. Finally, my experience with REVIT structure in particular, worked with REVIT since 2005 with several buildings, and we have used it successfully on many projects. Yet there are lessons to be learned along the way. Some of these are that we need continuous coordination of BIM between all the disciplines to keep everyone up to date. If in case that you have a detail, anything that you can detail using a typical detail or the sort, you can skip modeling it in Revit, such as miscellaneous steel. Maybe you don't want to put all these small angles and so on. Or and then you can insert CAD details. The other option is you can insert the CAD detail as an object into Revit. So you save on time and on space. Also, one of the things that you can, for future to be done is we need to make the process of modeling the rebars in concrete something that is easier to implement and so on. So this is something for the future to be worked on. In conclusion, we can say that BIM is the future of the industry, and the question that the concrete industry should be asking is how effectively to implement BIM rather than whether to adopt it or not. Thank you for listening.
You're running a bit late this morning.
Okay. Thank you.